Well, welcome to lecture 22 on quaternions. Let me give you the definition. So, a quaternion is something of the form alpha naught plus I alpha 1 plus j alpha 2 plus k alpha 3, where alpha 0, alpha 1, alpha 2, alpha 3 are real numbers, and I, j, and k are so-called imaginary units. They satisfy I squared plus equals j squared equals k squared equals minus 1, just like the complex numbers, but not like the complex numbers, actually quite different. Ij is equal to minus ji, and that's equal to k. Jk is equal to minus kj, which is equal to I. And ki is equal to minus ik is equal to j by definition. All right. And we use this funny looking h for the set of all quaternions. So we say alpha is a quaternion with the real part of alpha equal to alpha naught. The conjugate of alpha, which I'll denote alpha bar in this lecture, you just put, oh man, I got my, oh well, I don't have my correction pen, we'll just have to suffer the scribbling the mark there. So the conjugate, you just put minuses on the imaginary units like that. So for alpha and beta quaternions, we define multiplication in the natural fashion, and by that I mean you just multiply normally, keeping in mind the new funny rules for like ij is equal to minus ji and such. So here's how it looks. Basically this times that, what I've written down here is just the natural multiplication, like distribute, and for example, like I times I is minus 1, j times j is minus 1, k times k is minus 1. That's where these three minuses come from. To get I, you can either do k times j, which is the alpha 3, alpha 2, just a second here. Please tell me I haven't made a mistake. You can either do, j times k gives me I, or k times j gives me minus I. So that's why I've got alpha 2 beta 3 minus alpha 3 beta 2 I. There's also the terms I wrote down here for the I component, like alpha 0 times beta 1 and alpha 1 times beta 0. Those are also with the I. And so yeah, this is just, this is how you multiply quaternions, which basically just multiply like usual, keeping in mind that, ji is equal to minus k, kj is equal to minus I, ik is equal to minus j, and ij is k, jk is I, ki is j. Now if you remember your calculus 3, that's the same as the rule for like the cross product, right? The cross product of I hat and j hat is k hat and such. And so there's a reason for that. We'll discuss that as we go on here. So the length or the norm of a quaternion is just the sum of the square root of the sum of the squares of the components. So that would be alpha 0 squared plus alpha 1 squared plus alpha 2 squared plus alpha 3 squared, like that, right? All right, so let me point out some things here. If we define, I'm going to use a new notation here. Let me just scooch this up a bit. There we go. So if I have alpha as this, I define alpha vector to be the part with the imaginary units, and beta vector would be the part of beta with the imaginary units. So when I do alpha dot beta from calc 3, that's alpha 1 beta 1 plus alpha 2 beta 2 plus alpha 3 beta 3, maybe you remember. And the cross product of an alpha and beta as vectors is defined like such, right? And so if you go back up here and look at this, what you've got is minus the dot product plus the cross product, actually. So if we have no alpha 0, no beta 0 component, or you can just focus on the vector part if you like, the vector part of alpha times the vector part of beta is minus the dot product of alpha and beta plus the cross product. So the quaternion multiplication simultaneously includes both the dot and cross products that we learned in calculus 3. That's pretty, I remember when I discovered this as an undergraduate, I first learned about this, I was like, wow, that's really cool. It is really cool. It's also kind of cumbersome. I mean, if you think about it more, you'll eventually realize that the vector notation is far better. But well, anyway, Quaternions it's a kind of like a cult movie or something. It has a certain set of devoted followers that, you know, speak its praises. It does have its role. I mean, Quaternions are an important example, as I'll explain here as we go on. So anyway, if we have alpha naught plus alpha vector, beta naught plus beta vector for alpha and beta respectively, when we multiply those Quaternions, we get the product of the scalar parts, alpha naught, beta naught, and I mean the product of the real parts, so alpha naught, beta naught, minus the dot product of alpha and beta vector parts, plus the cross product of alpha and beta vector parts, and then plus like the scalar multiple of beta by alpha naught plus the scalar multiple of alpha by beta naught. All right, that's what you got. And so here's a couple of concrete examples. If I have 1 plus I plus j and beta is 3 plus 4k, when we multiply 1 plus I plus j times 3 plus 4k, I just distribute it, and don't try to follow my exact pattern. Like I sometimes make poor choices in like my ordering of things. The point is, you multiply it out, and it's the same rule as usual. You got 3 things here, you got 2 things here. You ought to have 6 terms in total, you know. 1, 2, 3, 4, 5, 6. 6 terms in total. And anyway, once you take into account the fact that ik is equal to minus j and jk is equal to I, certain terms combine, and you're left with 3 plus 7i minus j plus 4k. All right, so that's example 1. Just wanted to give you a concrete Quaternion multiplication. There it is. Quaternion addition and subtraction I don't really talk about because, I mean, come on. You just add like terms, you know, there's really not much to talk about there. Anyway, if I multiply I plus j times j plus k, then I get 4 terms, right? I get ij plus ik plus jj plus jk. Now, the jj is minus 1, the ij is the k, the jk is the I, and ik is minus j. So there you have it. And so, you know, that's not an accident. The dot product of 1, 1, 0 with 0, 1, 1 is 1, so you get that minus 1 here. And if you were to calculate the cross product of ij and j with j plus k, you'd get I minus j plus k as a vector there. This vector, I minus j plus k, is perpendicular to both I plus j and j plus k. It's the cross product. All right, anyway, don't worry. I'm not going to put a Calc 3 problem on your final in this course or anything. Don't despair. I'm not going to do that to you. Reverting to the vector notation might help, right? So this is that, and j. I should have pulled this paper down a minute ago. So I got 1, 1, 0 for I plus j. I've got 0, 1, 1 for j plus k. So the dot product of this and that is 1, whereas, I don't know if you remember or not, but the cross product, we a lot of times teach students this snazzy determinant formula, which is kind of sketchy because it's got vectors in the first thing and numbers in the second and third rows. So technically speaking, this determinant is, for most people's formalisms, this determinant is, technically speaking, really not allowed. But anyway, there does exist a certain sophistication where that determinant's a legitimate object, let's just say that. Anyway, so pedantic comments aside, when you calculate this determinant, you do the plus minus plus thing, and then you calculate the 2 by 2 determinants of the minors. And so anyway, you get this 1 minus 1, 1, which of course is what we just got from multiplying the Quaternions up there anyway. All right, so Quaternions are pretty neat. They're not that hard to multiply. I won't really say much about it in this lecture, but people are still interested in Quaternions for the sake of, for example, computer graphics. There's something about implementing rotations with Quaternions which makes them a little bit better for like graphics engines and such. Now personally, if you asked me to explain that, I probably couldn't at the moment. I've had engineers come and ask me to explain that to them before, and I've never actually quite cracked that just yet. I think of rotations in terms of matrices, to be honest. But there is a way of thinking of them in terms of quaternions, which is apparently superior to the matrix way of thinking in certain regards. So I'll just say that. Not really a number theory comment, but a comment. Now, so quaternions, what are they? Well, they predate vectors about 60 years. Hamilton's discovery of the quaternions was about 1840. And they were only really replaced by the vector notation that you learned in, say, Calculus 3 around 1900. I think this was particular the school of Gibbs and Heaviside. So the usage of ijk for vectors is actually in honor of Hamilton's quaternions. And, well, I would add that it's a bad notation because, you know, oops, sorry, the sun is really bright out at the moment. I actually prefer to use a notation for vectors that reflects the coordinate system being used. So, but anyway, again, really off the topic of number theory. Anyway. All right, so you might say, well, these madcap quaternions, how do you know they even exist? What do you mean quaternions? That's just a bunch of made-up nonsense, a bunch of mathematical nonsense. But you can, goodness gracious, I need to, the sun is really quite something at the moment. I need to, like, fix that. Just a second. Maybe if I do that. Aha, there. So this is the matrix representation of the quaternions. And so if you doubted the existence of the quaternions, you could say, well, quaternions are particular 4x4 matrices, and if you look at these particular 4x4 matrices, they multiply just like quaternions multiply. So you could say that quaternions exist because these matrices clearly exist. You know, that's one way you could do it. But for our purposes, let's just think of the matrices as a nice model of the quaternions. And I could show you how to derive this, but that would kind of take us off topic here. So let me just say that you can derive this in a certain way. If you're interested, ask me. But if you define 4x4 matrices like this to be the representation of the quaternion, alpha naught plus I alpha 1 plus j alpha 2 plus k alpha 3, right? Then there are some various things that happen. For one thing, the transpose of the matrix, flipping over the diagonal, if you look at it, it's actually the matrix of the conjugate of the quaternions. That's kind of neat. Furthermore, the multiplication of matrices encodes multiplication in the quaternions in the sense that if you take the product of the matrix representing alpha and the matrix respecting beta, it's the matrix of alpha times beta. All right. So, you know, that would make a pretty good homework problem. I shouldn't say it would make a pretty good homework problem. It would make a pretty tedious homework problem. But if you're serious about this stuff, you should work that out. Yeah. I'm not saying you need to work that out necessarily. I know that the end is near here. So anyway, what's really neat though is the meaning of the determinant of alpha. So let's calculate the determinant of the matrix. So here it is. So it's a 4x4 matrix. So the determinant is, yeah, I'm expanding across the top row, alpha naught, determinant of the 3x3 that crosses out the, you know, this one and that one. It leaves me this 3x3, which I put here. And then with alpha 1, we cross out this one and this one, everything else is left. You know, that gives me these guys. And then for alpha 2, I cross out this row and the first row, I mean that column in this row. And what's left is this and these guys over here, which I put down here. And then alpha 3, cross out that column and this row, which just leaves you the lower left block here. And the rule for the you know, Laplace's expansion by minors for the determinants, it goes plus, minus, but there's minuses up here, so it goes plus, minus, minus goes plus, minus, plus, minus goes minus, and what did I say, plus, minus, minus, minus goes plus again. Which is good, because those are exactly the signs we need when we expand this all out for things to cancel out nicely. Now let me whoop, scooch this up here a bit. This calculation's a little much, but here it is. So when I calculate out these determinants, and so it's a 4 by 4 determinant, so it's got 24 terms. 4 factorial is 24. And of those 24 terms, you got this guy and this guy canceling, this guy and this guy canceling, this guy and this guy canceling, this guy and this guy canceling. So that's what? 1, 2, 3, 4, 8 terms cancel, and that leaves you 24 minus 8, which is 16 terms left to group. And those 16 terms actually end up giving you this sum of squares times that sum of squares, which is pretty cool because that's the length of the quaternion squared. So the determinant of the matrix of the quaternion is actually the length of the quaternion squared, which makes this particular matrix representation very nice because it nicely interfaces between the world of matrix multiplication and determinants and the quaternions and their norms. So just to summarize what I got here so far, and admittedly I have not proved all of this. Well, the thing I didn't prove was number 2, and that would require me about a page of calculation, truth be told. But it's true. You can check it if you want. And what else I can say is, well, if we calculate the a quaternion times its conjugate, something kind of neat happens because we get like alpha naught, and then you notice that the scalar multiples of alpha naught with alpha vector, they add and subtract in the product, so those cancel, and then you get the product of alpha with alpha vector with alpha vector minus. But remember, that gives us the dot product of alpha with itself plus the cross product of alpha with itself. Hey, but the cross product of any vector with itself is 0, so that's 0. And you're just left with alpha naught plus alpha dot alpha vector, which is the length squared of the quaternion. So this is another thing we get. The length of the quaternion squared is the product of the quaternion and its conjugate. All right, so if we put this together with what we just learned about the rule for matrices, then we're going to be able to derive that the length of the product of two quaternions is the product of their lengths, which is an amazing identity, which is not true for almost every algebra. There's a very precious small set of algebras for which it's possible to define a norm on the algebra. That is a concept of length, which plays nicely with the concept of multiplication. These are special and rare examples. But here's the proof that it is such the case. It is the case for quaternions. So the norm is, of course, not negative. So we can check that the norm of the length of the product is the product of the lengths, if and only if the length squared is the product of the lengths squared. Product of the squared lengths, I guess I could say. Anyway, so here it is. Length of alpha beta squared is the determinant of the matrix of alpha beta, but by the thing I didn't prove, but it's true, that's the determinant of the matrix of alpha times the matrix of beta. But then by properties of the determinant of the product is the product of the determinants. That is a non-trivial identity. And so that gives us then that the length of alpha squared times beta squared is equal to the length of alpha beta squared, which is what we're setting out to prove. Now that is actually very interesting because that is essentially the 4-square identity. All right, but we'll come back to that. I wanted to mention, you can come up with a matrix-free proof that the product of the lengths is the length of the, the length of the product is the product of the lengths. Here's a matrix-free proof. I first of all prove, this is kind of surprising, the conjugate of the product is the product of the conjugates in reverse order. That's a little bit surprising and it catch you off guard if you're not looking out for it. But for quaternions, because the quaternions are not, they don't have to commute. All right, there's an anti-commutativity of the imaginary units. I times j is equal to minus j times I, and that ends up switching the order. So let's see why. So alpha conjugate is alpha naught minus alpha vector. Beta conjugate is beta naught minus beta vector. And remember, the product of alpha and beta is minus alpha dot beta plus the cross product of alpha and beta. So if I multiply alpha beta, I get all this stuff right here, right? scalar multiple of, the product of the real parts, scalar multiple of alpha naught times beta vector, scalar multiple of beta naught vector times beta naught times alpha vector, minus the dot product of alpha and beta plus the cross product of alpha and beta. Now if you think through this, when we take the conjugate of it, it does nothing to the real part, like alpha naught, beta naught, and alpha dot beta. Those are real, right? But the beta vector and the alpha vector, they've got an I and a j in them, and so when we take the complex conjugate, we end up with a minus there and there, and we also end up with a minus for the cross product of alpha and beta there, like that. And so on the other hand, if we calculate beta bar times alpha bar, pretty much the same calculation, right? We get this. But notice that to make the final step, I switched the order of beta cross alpha to minus alpha cross beta because the cross product anti-commutes, and then star is equal to star star, which gives us this is equal to that. And then once you know that the product of the conjugate is the conjugate of the product is the product of the conjugates in reverse order, it all comes together pretty nicely down here. See, because the length of alpha beta squared is alpha beta times the conjugate of alpha beta, which is alpha beta beta bar alpha bar, but beta beta bar is the length of beta squared, which then that's a real number, so you can pull it out to the front, and then you get alpha alpha bar, which is the length of alpha squared, and so there you have it. So if you didn't know about that fancy matrix trick I showed you, you could still sort through it in this way. All right, just mentioning. All right, so let's get back to the number theory at last. So S4, all right, is the set of numbers that are formed from the set of 4 squares, right? So it's the 4 square set. Isn't that a game? I don't know. Anyway, so theorem, S4 is closed under multiplication. In other words, if A and B are in S4, then AB is in S4. So the proof is given here. If we have A and B in S4, where I'll couple things up here to keep me on track here. So we have A is the sum of 4 squares, B is the sum of 4 squares, and I'm using the notation alpha naught, alpha 1, alpha 1, alpha 2, alpha 3, and likewise beta naught, beta 1, beta 2, beta 3 to anticipate rewriting them using Quaternion math, So, so here, of course, they're integers, right? The alpha i's and the beta j's, they're all integers. And we can construct corresponding Quaternions, all right? Alpha equal to alpha naught plus I alpha 1 plus j alpha 2 plus k alpha 3, and likewise for beta. And then with respect to that construction, the length of alpha squared is A, and the length of beta squared is B. All right. So then what is A times B? Well, A times B is the length of alpha squared times the length of beta squared, which we just got done proving is the length of alpha beta squared. And what is that? Well, it's this. Now, how did I get that formula? I went back to like page 1, all right? Back to page 1 here. Oops, that's not page 1. Come on, page 1, show yourself. Page 1. So back to this formula right here, and I collected all the real part, that square that, the I part, which is this and that, the j part, which is this and that, the k part, which is this and that, and I put those together here. All right, so this is using formula from 1. All right, so there it is, the real part squared plus the I part squared plus the j part squared plus the k part squared. That's what it is, and that's of course in S4. So there you have it. S4 is closed under multiplication. But this proof, it does more than just prove the closure of S4. It suggests a method for writing numbers, right, as the sum of 4 squares in a kind of sneaky way. Or generating new numbers that are sums of 4 squares from old, much like we did with the Gaussian integers. So let me show you some of that. So like here's one. So 7, I'll get it here eventually. All right, here we go. 7 is 1 squared plus 2 squared, 2 squared plus 1 squared plus 1 squared plus 1 squared. 10 is 3 squared plus 1 squared plus 0 plus squared plus 0 squared. Excuse me. So I can let alpha be 2 plus I plus j plus k. And 7 is alpha alpha bar. And I can let beta be 3 plus I, and then 10 will be beta beta bar, right? So how about 70? Well, 70 is 7 times 10, right? But it's also the product of these here Quaternions. And I don't really need to, I only need to calculate half of it. I can just leave the alpha beta bar out to the side, okay? And but multiply alpha and beta, and when I do that, I make a stupid mistake. I have to write out the answer back in pen, as you can see. But setting aside stupid mistakes, it multiplies out pretty nice, pretty easily, group things, and eventually you get 5 plus 5i plus 4j plus 2k times its conjugate, which gives you 5 squared plus 5 squared plus 4 squared plus 2 squared. In other words, 70 is 25 plus 25 plus 16 plus 4, which is true. But you can do more, right? You could find other ways to write 70 as a sum of 4 squares by grouping the numbers a little bit differently. See, if instead of grouping alpha with beta, if I group alpha with beta bar, see alpha beta bar, and then what's left over is beta alpha bar, but that's actually the conjugate of alpha beta bar. So it's a number, quaternion times its conjugate, which means it's the sum of squares. So I can just focus on the alpha beta bar and just let this ride over here, whatever. And when I multiply these things out, all right, and collect terms, I get 7 plus I plus 2j plus 4k, which is 7 squared plus 1 squared plus 2 squared plus 4 squared. You know, this is a different way of writing 70 as the sum of 4 squares as compared to what I had before, which was 5 squared plus 5 squared plus 4 squared plus 2 squared. So if you want to, you can play this game to find many ways to rewrite a particular kind of number as different sets of 4 squares. Much like we could play this game with the Quaternions, with the Gaussian integers, to rewrite things as sums of 2 squares, right? So let me tell you a little bit more about the interplay between Quaternions and the Quaternions and the Gaussian integers, all right? So the naive generalization to the Gaussian integers would be z adjoin I, j, and k. That's a subset of the Quaternions, right? But as it happens, z adjoined with I, j, k does not have a division algorithm, and it turns out you have to look at something called the Hurwitz integers. Now, Hurwitz integers are the form a plus bi plus cj plus dk, where a, b, and c and d are multiples of integer times a half, which means that they can either be like a half or 2 or 3 or 3 halves. All right. For example, 1 half plus 3 halves I minus 3 halves j plus 8k is a Hurwitz integer. All right. And so I'm using this funny looking h just to have a label for Hurwitz integer for this discussion here. All right. That's not a standard notation. It's just what I'm making up for this particular page in this particular discussion. Okay. Certainly the Hurwitz integers include the naive generalization, z adjoin ijk, but it's got more, right? And it turns out that the Hurwitz integers do form, I would say they form a Euclidean domain, but I can't quite say that because they're not a commutative ring, all right? So, but they do have a division algorithm in a sense. You gotta be careful. There's a difference between left and right divisors because Quaternions are non-commutative. It's really quite a mess, what are Hurwitz primes. But you can factor Quaternions using these Hurwitz primes. And there is a prime divisor property. And so ultimately this technology is part of what's used to prove the four-square theorem, which is that every natural number is the sum of 4 squares. All right. Now, if you'd like to see some details on that, you can look at Chapter 8 of Stilwell's Elements of Number Theory. It's got it in there. But I will just tell you this: the Hurwitz primes and all that. It's a lot. So just a little more history. Probably should have started with this, but oh well, better late than never, right? So the interplay between complex numbers and sums of squares was well known by the 19th century. I mean, things about sums of squares was known to the ancient, right? I think we talked about that before. The Greeks, the Diophantus knew about this stuff. Certainly those Brahmagupta and the other great ancient Indian mathematician that I can't remember the name of. Sufficient to say that there are many brilliant ancient mathematicians who worked on this and have been forgotten. So anyway, so sums of squares, well known by the early 19th century. But and so also the interplay between the complex numbers and geometry of the plane was also well known, right? So like complex numbers in the plane, every complex number corresponds to like a rotation and a dilation. For example, when you multiply by I, if you look at it, what it does is it rotates the complex number by 90 degrees, you know? So it's natural then to want to invent a system, multiplication on R3, which somehow captures like the rotations in 3 dimensions, just like complex multiplication captures rotations in the plane. So after about a decade, actually 13 years, Hamilton worked on finding a multiplication for R3, and finally, after 13 years, he realized that it wasn't going to work, and he decided to add time to his 3 spatial dimensions. And once he did that, it kind of unfolded in front of him. And the multiplication on R4, which he discovered, is the Quaternion multiplication that we've discussed in this lecture. You know, as is often the case, you know, so it was 1843 when Hamilton made this discovery, and there was another mathematician by the name of Rodriguez who actually used that Quaternion multiplication to study rotations in R3 in 1840, but Hamilton is generally credited with the Quaternions because he's the one that popularized the idea and, you know, explained their importance more so. But you know, if Rodriguez did this, it stands to reason that it probably were other people that kind of had this idea. But anyway, and also of note, as is often the case, Euler knew it before he should have. And so Euler's like a full 100 years before this history. He knew the 4-square identity, just like the thing we wrote on the other page. Where was it? Like 3 pages back. Where's that thing? Where'd it go? Oh man, I've lost it. Where'd you go? Come back to me, 4-square identity. Oh, rats. Oh, here. So like Euler just saw that if you multiply, you know, alpha 0 squared plus alpha 1 squared plus alpha 2 squared plus alpha 3 squared times beta 0 squared plus beta 1 squared plus beta 2 squared plus beta 3 squared. When you multiply that out, you can rewrite it as some of these 4 squares. Like Euler's just like, yeah, I could see that. Because he was Euler. But Euler didn't, as far as we know, knew the Quaternions, but he did have the algebraic wherewithal to see the 4 squares identity. And also it was proved, I think, or known at least to Legendre, that there did not exist a 3 squares identity. So, you know, Hamilton apparently working on this problem for 13 years didn't really, he wasn't very, very well acquainted with what was already known. Perhaps he only found out about these bits of history after he actually did what he did. Oftentimes that's the case with mathematicians. Like, you know, it's easy to like sort of cast aspersion on somebody like, oh, they should know that, it was already known. Like, well, no, people get an idea and they chase it and they chase it and they chase it, and a lot of times they don't try to take a look and see what was already done. I mean, it's not not at all uncommon for things to be discovered, rediscovered by different people. It's getting harder to excuse with the internet these days, but still it happens. Anyway, so just to reiterate here, the Quaternions are a very special object. They're almost a field. In other words, a field is a commutative ring with identity in which every non-zero element has a multiplicative inverse. Quaternions are a ring with identity where every non-zero element has a multiplicative inverse. It's just that the multiplication's not commutative. So that's why it's sometimes called a skew field. It's almost a field, right? And because of this, there are many things that you can set up in the Quaternions that are like this construction for fields, but not quite. So it's just right on the edge of not working. Anyway, past the Quaternions, there's something called octonions. Octonions are an 8-dimensional space that was discovered by Cayley and Graves independently. And these octonions are non-associative, which is worse. I do believe they're what's known as power associative, though. And then, it wasn't just that Hamilton failed on the, failed to find a multiplication on R3 because of lack of imagination. As I mentioned, Legendre also knew that there did not exist a 3 squares identity, but it was proved actually by Frobenius in 1878 that the reals, the complexes, and the Quaternions are the only finite dimensional associative division algebras over R. So it means what it says. It's an associative multiplication. Division meaning every non-zero element has a multiplicative inverse, right? Over R, that means that the real numbers are in the center of it, so real numbers commute with everything in the algebra. So Frobenius is an important mathematician of the 19th century. He maybe was the first guy to really do linear algebra carefully, right? I think a lot of our ideas in linear algebra maybe were first really fleshed out by that guy. I mean, linear algebra is everywhere in ancient mathematics, here or there, but Frobenius did a lot of things in general that had only been done in cases before. Hurwitz, 1898, showed that there exists a k-squared identity for only k equals 1, 2, 4, and 8. Stated a different way, Hurwitz showed that the only normed division algebras are those of dimension 1, 2, 4, and 8, which are the reals, the complexes, the Quaternions, and the octonions, up to isomorphism. And so normed division algebras are those which have a multiplicative norm, but the multiplicativity of the that's a mouthful. The multiplicative property of the norm is the square sum of squares identity, as we saw in this lecture. So anyway, probably don't have any homework for you much on this. I might ask a question on the final. If I was to ask a question on the final, it would probably be something like example 3 to example 4 kind of thing. All right, so if you understand example 3 and example 4, you should be okay for the question I ask about Quaternions on the final. So I would think. Anyway, thanks guys.